All right, let's talk about something so basic you probably haven't even thought about it since you were a kid. Primary colors. For paint, we all learned red, yellow, and blue. Simple. But when it comes to light, the story changes, right? We're always told it's red, green, and blue. But what if that's not quite right? What if we've been missing a piece of the puzzle all along? I mean, think about it. The screen you are looking at this very second is creating every single color you see by just mixing red, green, and blue light. It's called the RGB model, and it is literally the foundation of our entire digital world. It's in your phone, your TV, your camera, it's just everywhere. And it feels totally solid, doesn't it? I mean, it works. But what if that model, as universal as it seems, is actually incomplete? What if it's more of a convenient shortcut than the actual fundamental truth about light? So let's go looking for the cracks in that color code. We're going to dive into a really fascinating argument that suggests our trusted three-color system, well, it just doesn't quite hold up under pressure. Okay, so here's problem number one. Any system for creating color, whether it's a printer or a screen, has what's called a gamut, basically the total range of colors it can possibly create. And the RGB model, it has its limits. There are colors out there in the real world that your screen literally can't show you. A classic example is a pigment called gamboge yellow. It's this incredibly pure, vibrant yellow that a simple mix of red and green light just can't nail. And yeah, just to lock that term in, gamut. It's the entire color palette a device can work with. So if a color is out of gamut, the system just gives up and shows you the next best thing. And this isn't just some minor technical issue. It's a huge clue that maybe we picked the wrong primary colors to begin with. And the clues just keep coming. Let's look at color blindness. A lot of folks who have trouble telling red and green apart can still see blue and yellow perfectly fine. Now here's the really interesting part. Scientists often compare this type of vision to a printer that's run out of its yellow ink cartridge, not its green one. Why yellow? It kind of suggests yellow is playing a much more fundamental role in how we see than our RGB model gives it credit for. So, if our screens aren't giving us the full picture, where else can we look? Well, the next clue pops up in a place you would never, ever expect, inside of rocks. Yup, rocks. There's a whole field of science called petrography, which is basically analyzing minerals by seeing how they mess with light. Scientists take these super thin slices of rock and shine a special kind of polarized light through them. And as that light passes through, each mineral creates this unique color signature, almost like a fingerprint. To read that fingerprint, they use a very specific and very old tool. And this is it, the Michel-Levy chart. Geologists have been using this thing for over 100 years. It's like a standard reference guide. It simply maps out the colors that appear when light gets split by a crystal. But hiding in plain sight on this everyday scientific chart is a clue that seems to turn our whole understanding of light on its head. Okay, so follow the light with me here. As it starts to pass through the mineral, look what happens on the chart. First, you get this big, wide, strong band of yellow. Then, right after it, a big, wide, strong band of cyan. So, where's green? Our supposed primary color? Well, it's there, but it's just this weak, pale little sliver in between yellow and cyan. If green were really a primary building block of light, shouldn't it be just as bold and obvious as the other two? This one little observation from a century-old geology chart leads to a pretty radical proposal, one that could rewrite the rulebook on color theory. This is the big idea. The Michel-Levy chart seems to be screaming at us that light isn't made of 3 primary colors. It's made of 4: red, yellow, cyan, and violet. These, the argument goes, are the true, fundamental building blocks of the light we see. So let's just put these two models side by side to make it super clear. Our conventional RGB model says green is primary, but this proposed model says no. Green is secondary. It's what you get when you mix the 2 true primaries of yellow and cyan. And if that's true, it would suddenly explain everything, why green looks so weak on that chart and why our RGB screens struggle to make certain colors. But this isn't just a debate about color. This rabbit hole goes so much deeper, and it raises some really big questions about how we even approach science in the first place. To understand this, we've got to go back in time. When the brilliant physicist James Clerk Maxwell was working on this stuff, he ran into that same gamut problem. He realized that no 3 real colors could mix to create all the others. So he made a choice. Instead of looking for a fourth primary, he just redefined them as abstract mathematical concepts, imaginary colors that made the math work. It was a clever engineering fix, but it took color theory a step away from physical reality. And that leads to this pretty provocative claim that maybe modern science sometimes cares more about engineering solutions than finding fundamental truths. We build things that just work. The RGB model works well enough for our screens, but is it actually true? It's kind of like Ptolemy's old model of the solar system. It had all these crazy, complex circles on top of circles, and it was actually pretty good at predicting where the planets would be. But the underlying theory, it was completely wrong. And that's why Johannes Kepler is such a hero in the history of science. For centuries, everyone was obsessed with the beautiful, elegant idea of perfect circular orbits. But Kepler dared to actually look at the data, at the physical evidence, and he proved that planets move in ellipses. That's what true scientific progress looks like, being willing to abandon a good enough theory for one that actually matches reality. So we're left with this thought. An old chart used by geologists to look at rocks might actually hold the key to rewriting our understanding of light. And if something that fundamental, something we teach to children, is still up for debate, what other settled science is just sitting there, waiting for someone to come along and look at it with fresh eyes?